Hello, everybody. Hello. We've got, got the feedback going there. Okay. Hi, everybody. Let's see if we can get this to work. So we're back kind of the old set a little bit, but I am hoping that this will work out better for diagrams and what we want to look at today. And since yesterday we went over the microscope and how to set that up with your, hi everybody, hi Gerda. So yes, since we went over yesterday how to set up your microscope on your phone, or one of the ways, I thought we, thank you, I thought we could look at a few different things with our microscopes. So I'm going to set it up, actually this is an idea that Scott gave me from a question he asked yesterday, of course. So I'm going to put the lens on this phone, and so we can see directly, or I'm going to let everybody here see directly what, thank you, what I've got here. So I've got a few different samples, and then I've got some diagrams, and hopefully that will be easier for everyone to understand. So one thing scared you nano-wise, gray goo. I'm not sure what gray goo is, but hopefully things at the nanoscale don't scare you. That's not my goal. So if anyone here is new, my name's Julia. You're following me here at Fine Woman, so you can find me. I'll turn this around quickly. You can find me here at Instagram or Twitter, and you can tweet me questions there as well, or you can just ask them here, and I've actually got a backup. Oh, I see, nanobots, interesting. Thank you. So you can tweet me or just ask the questions. Yeah, I've got a different setup here where I should be able to see the comments with a little bit of delay so that I can catch them if I miss them. So the other thing, if you don't understand something, hi Constantina, if you don't understand something, then please don't let me go on. Just tell me, type in 42, and then I'll stop and try to find a way to explain it to you. I'm well, thank you, Constantina. I hope you are as well. So I'm going to set up the microscope here. So if you remember yesterday, we took the lens, that little tiny lens, which I can show you right here just for scale. Now normally you don't want to touch optics with your hands, so don't do this too much, but here, that tiny little lens, very, very small. So I'm going to put this on the back of the camera here. You're going to see it go blurry for a second. But then, well, before I do that, I'll show you what we're going to look at. See if I can get this set up. So what I figured we could look at here was, cabled here, sorry. We've got that butterfly that I may have shown people before. We've got some crystals of unknown substance yet, but we'll talk about that in a second, if it can focus here. And there we go. And we've got another little creature there, a bug that I found. I thought we could look at up close, and some flowers. So eyes only on the bugs. So we'll see what this looks like up close. And I will put the lens on. And we're going to look at the crystals, actually, so hold on one second. And we're going to see if, there we go. We're going to see if, what they look like when we get really, really close, and then we'll go over, yeah. So, there we go. So that is actually, anyone want to take a guess what that is? You saw it from afar, thank you. Anyone want to take a guess? Salt! Yes! Yes, we got an answer. So this is just normal table salt from the grocery store. So not sugar, actually. This one's salt, although it does look kind of large for salt grains. So if we look at these really, really small pieces, I had some nice examples here. There we go. So that small piece, they tend to either have, they're either going to have, hi everybody, yeah, the Heisenberg special, that's funny. Nope, not jewelry. So this is your regular or normal, not even organic table salt here. Sorry, I'm trying to keep this steady. And the reason that it looks like crystals is because that's exactly what it is. It's a solid, and solids have to form, or if it's actual solid, right, they have to be in some sort of stable, organized structure to remain solid. So this right here is actually sugar, Nolan. I know you took a guess earlier. So this is sugar. Now this is really fine sugar, so this has actually been ground. Yes, so I am using the microscope that we set up yesterday, Fred, and I was just looking, we were looking at a couple different things to see what they look like up close. So this is sweet, yes, very nice. This is sugar, and this is the salt, and what you see is that when you break up these crystals, they fall into, yeah, so some of those are nice cubes. They actually break up, it does look more jagged. I was surprised by this. So this is the Trader Joe's type of just regular salt. So they may have some other, it's not the organic, so I would imagine it's just regular old table salt. But I'm glad, yeah, well, welcome to this science soap. So that was salt and sugar. And those are crystals, so solids. And solids, when you, for all crystals really, when you break them apart into pieces, each smaller piece is going to look like the larger piece. So it's going to, in salt's case, it's usually more cubic, and I'll show you why in just a second with a couple of diagrams. But when you, yeah, I think it's pretty neat. It's because this is regular old table salt, obviously not expensive, and something you probably have around the house. And that actually, so the edges of it, you'll see have these kind of jagged, more cubic shapes sticking out from various sides. But so we can take a look at a couple just organic matter here just for the fun of it, and then I'll show the diagrams just to look at the salt and the structure and why it actually is looking that way. So, okay, so we'll tip it over here. So here's this wood, and then I'll take that lens off, we can look at it again. So this is this piece of bark I had here. If we can get kind of close, there we go. Yeah, so I have a couple of pieces of scrap metal I think I had on here, just, oh, thank you so much. Yeah, so we're just looking at lots of things up close. I missed who asked that, sorry. But this is just a piece of bark, and so that looks pretty cool. This is organic matter, and this is that bug I found. Oh, he looks gross up close. So that's just a regular old fruit fly. And he's not very happy because he's no longer alive. But yeah, it's pretty gross. And then the butterfly wing I thought was also pretty neat. So I'll come over here and see if we can see that pretty close. So now this butterfly wing I discovered, yep, it's a fruit fly. Yeah, absolutely we can do that. I'll do my hand here if we want to look at skin or something. But this, unlike, so you can kind of see that these butterfly wings, unlike the ones that we talked about, I think a couple weeks ago now, these actually have pigment in them. So they're not, so butterfly wings can actually give off color two ways, either by by pigments like this, or just by the way that it scatters light. So it actually doesn't have color, but it looks like it has color because, it looks like it has color only because it has very fine lines about, yeah, so it has very fine lines that will scatter light that comes and hits it, so it doesn't actually have color itself. So those are the two ways that butterfly wings have. Why do they shed dust, wings? I don't know quite exactly what you mean, if they would shed dust more than some other. So no, that butterfly actually, this is the only one it was a beautiful butterfly I found that was already dead, and that one does have that has pigment in it, but there are other butterfly wings. I'm going to see if I can find out what types might be native here and find one that I don't have to harm and have it as an example. But the butterfly wings, the other way that a butterfly wing can have color is just by having these protein layers that are layered so thin that the light that hits it, the wavelength of light, is about the same size, and depending on the energy or the color, it'll scatter and bounce off at different angles and look like a different color to your eye. So I think I mentioned that before, but if anyone doesn't understand that or wants me to talk about that a little bit more, then please let me know. And so, yeah, so we'll take maybe another quick look at the salt again up close, and then I'll show you some of the diagrams and how those crystals form and how solids actually form and why they look the way that they do. Oh, I'm so glad. Thank you so much. Okay, so everything looks blurry because here I've got the lens on. So we're going to take one last look at our salt sample here. So this is our salt. So you can see all the crystals of the different size. This is not part of my job. This is just something I'm trying to, yes, transverse, not longitudinal. Thank you. Yeah, I'm just trying, I mean, I'm interested in science education and communication, and I'm a writer, and so this seemed like it made sense as far as the time when Periscope came out. So that is the cool looking salt. They do, and there's a reason for that, actually, Justice. There is a very good reason for that. And so you can see this is blurry until I take the lens off. There we go. So if we look all the way to the nano scale, and so I'll, sorry, I gotta get my setup here going again, then we're gonna look at what the crystal, yeah, tasty, especially in beef stew, etc. So, sorry, bear with me one second. This is a new setup stand here. I was hoping that would make things easier, but not always. There we go. Okay. Yeah, so I'm going to be uploading these videos to YouTube now as well. So thanks to both David and Claire, got a great tutorial on how to upload the videos with the comments on Apple. So that is really useful, and that's what I'm going to upload on YouTube and set up that channel. So I'll go over now. I have my diagram board set up properly, and true to form, I've lost the, there it is, the stylus. Oops. Okay, so what we have here, this, if you can see this, can everyone see this okay? I see the hearts. Thank you very much for that. So hopefully that means you understand, because those, I'm not too much into the numbers. I appreciate it, thank you, but if you can see it and understand, that's the best indication for me. So yeah, it was a great instruction today. Okay, great. So here, this is, if we look down at the atomic level, then when we say nanoscale, then thank you. Nano actually refers to a particular range of numbers as a fraction of a meter. So if we have 1 meter like this, we call this 1.0 meters, then a nanometer is going to equal what we call 10 to the minus 9, but I'll explain that here in a second. And then that's just going to be 1, 2, 3, 4, 5, 6, 7, 8 zeros, and a 1. So that is a nanometer in numbers. So if this is 1.0 meters here, then a nanometer is going to be 1 billionth of a, let's see, millionth is 6, billionth is 9. So we're going to go, yeah, it is pretty small. And so the distance from here to here is a few of those nanometers. So depending on the molecules that you're looking at, the general, yep, so it's 10 to the minus 9. That's where the nano comes from. So that means it's actually a prefix for ranges of numbers. And so for most solids, if you're looking at the atomic scale, then this is going to be in the a few nanometers. And so when you hear things in tech about nanoscale devices and nanobots and things like that, the real nanobots are about the size of a few molecules. So they're usually about 100 nanometers. So they kind of push it, you know, if you're a 1,000 nanometers, then, oh, I'm sorry, I missed that comment. If that was a question to me, I'll please ask it again. So I'll try to keep a better eye on the comments here. I'm getting used to my diagram board. But yeah, so the few molecules, that's going to be in the range of a few nanometers, whereas these nanobots and things, they're going to be in the range of a few hundred nanometers, and then if you have 10 to the minus 6, then we're going to call that micro. So that's a micron or a micrometer. Oops, can't really, oh, thank you. Yeah, teachers, I think, teachers can be really great, but sometimes if they just don't have the passion or the background. So let's see, micro. There we go. Okay, so the reason that these crystals, when you break them apart, they keep looking the same is because at the atomic level, that's what they look like. So for sodium and chloride, then so the micro is written like this, if that's what you meant with the U. So it's a Greek letter for to represent that, just to make it short. So in the salt case, we have NaCl, and so these guys are going to be that one. Is that it? Yes. Let's see. Yeah. Yes. This is going to be the chlorine, and these are going to be the sodium. And what happens is, so the sizes actually do matter. So the reason that chlorine is a bigger atom than sodium, and that's why it comes later on the periodic table. And the charge, the ions that we were talking about, oh my goodness, thank you. The ions that we mentioned yesterday, I don't know, is Pizza Pop-Tart, are you here, Freddie, today? You were here yesterday, and she's asking about how pure water actually will not, if you put your foot or hand in it, you won't be electrocuted because it doesn't conduct electricity. But the actual things in the water that conduct electricity are these ions. So it doesn't have to be salt necessarily, but salt is one very prominent one. And so salt water will conduct electricity very well, because what happens is when you go into water, then it looks more like this, where these guys are the water molecules here. And so the water molecules, because they have this funny shape, so they look like this, they have that funny shape, then just even drawn on this diagram, right, in space, they're going to have a very slightly kind of asymmetric distribution of these charges around the molecule. So even though the molecule itself is stable, it's good, and neutral, I mean, it's not going to have an extra charge or an extra electron or lacking an electron, the asymmetric shape gives it some sort of preference as to where it is relative to other charges and other things that might be in there. So what happens is these, it dissolves, not everything, but it dissolves a lot of things, and when people talk about acids and bases and pH levels, it's based on the concentration in water and these hydrogen molecules, etc. So, but I see, yes, dissolving given enough time. Except oil. So most lipids and things, it's not going to, water in particular, so you need something like an acid or something like that to break it up, or an alcohol. So, in water here, that's what's cool about it. So it goes from this solid, so when you make salt water, hey Jason, welcome! When you make salt water, we were looking at microscope things on the phone microscope, so I'm doing a little demo here for anyone who's just joining. Is oil conductive? That's a great question. No, I don't believe it to be so, unless it depends on the oil, and it depends on what you mean by conductive. So as far as putting 2 electrodes in, no, that's not going to do it for you. But there will be some, because of these asymmetric shapes, etc., then you can have some local charge effects. But more than that, I want to think about that for just a second. On purity of the oil, not necessarily on the oil, but in the water here. So the ability for it to conduct electricity here is going to be based on how much the ions here can move around, or how many ions you have to move around, because when this water pulls them apart, and this is just dissolving, so it goes from the salt, just like the rock salt in your salt shaker, to looking like this. These are the water molecules here, and these then can carry that charge. And that charge is then what electrocutes you if you have your hand in the bucket. So I'll put the lens back. We can look at salt if we want. Are there any questions while I got the diagram up where I can draw things? That kind of makes sense, and hopefully somewhat interesting, but there's things around your house, if you are able to make this microscope, that are going to be really interesting that you might not expect. Because I know Dominic does great things with the telescope, and Scott as well, and so I think I would love to bring attention to the things at the very small scale, because at the very small scale, I think there are things that are just as interesting. So I'll put this lens back on. I didn't see any questions, so please feel free to ask them, but I'll put this back on just one last time, and then we can look at the salt again. So everything goes, okay. So when we look right up close, and we can see all those little salt crystals. Oh, you're just listening? Oh, well, I will describe these salt crystals. They look like small crystals. But, yeah, it depends on the purpose, though. So for this, definitely some interesting things going on, and it's all relative, Fred. All relative. So, yes, so kosher salts, so all salt, if you're talking about table salt, the base, the thing that gives you the taste on your tongue is sodium chloride, so that's what this is. If you talk about the salts that are like the pink ones and the fancy ones that you get at Whole Foods, etc., those are going to have other minerals in them, and those impurities, those are technically impurities, then that will give it a color, and that's what's going to it'll have something other than just the sodium chloride. And to magnify the salt water, yeah, that sounds right, Lariat. The salt so that is the salt all broken up. So I'll show you without the lens here. But the salt water you can magnify, but not with the at-home devices. So here's for scale, a little flower there. It's kind of out of focus. So that's the salt. And the water. So water is a very hard thing to model and look at. So people are very interested in looking at water, especially the surface, because that asymmetry, that shape asymmetry, that one right there where I drew right here. So this kind of asymmetric shape here, that makes these hydrogen bonds, they call them, and so water has that creeping effect. It'll go up a straw, or it will climb the walls of glass, and that's because the water likes to stick together, that surface tension, and it's because of this asymmetric shape. So it's really interesting to look at the surfaces, but as far as looking at it up close, people can look, yeah, exactly, capillary action. So people can look at salt, and it's polar, yep, so that asymmetric shape, that's another way to say it, so that means that it will have a preference if you put it in the presence of these charges, for instance, or an electric field or something, it'll have a preference to the direction. And so that's that polar aspect. But the surface tension is a really interesting thing. Now, to look at it very close, you can look at water as in ice form. And people do. People study things that are in ice, trapped in ice, or just the ice itself to try to get a lot of information about the water and the surfaces. But it's really hard to look at any liquid very closely as an image, because most of the time when you have to look at something that closely and see it with a microscope, for instance, you need it to stay still. And water, by nature being a liquid, is not going to stay still for you. So you need it to kind of hold still and be very cold a lot of the times, because the colder something is, the less it's going to move around and shake and vibrate. So, yeah, exactly. So you can freeze it, and people do they study water, or ice, I should say, and then they can they'll put things in the cage, they call it, of ice. So they put little molecules, so let's see, different gases, methane, for instance, they'll put in water cages or ice cages so that they can study this and see the different interactions. It does change the structure, but it doesn't change the properties of the molecule itself. So we can study the molecule and get understandings from those studies without actually needing to see it in, but it does limit us. So we might not be able to see water in its liquid form in that way, but it does give us a lot of information. Oh, very good question. So yeah, so the water is formed by a couple of different processes. Well, let's see. hydrolysis, I believe, so this is chemistry that I'm not going to remember so quickly, but it will come out of a lot of processes, and thank you very much. It will come out of a lot of processes as a byproduct sometimes. So if you have reactions that will form, so there's many different reactions that will give you back water or give you water, but it depends on the situation. So two H's and an O will bond together a lot of times as kind of the leftover of something, or if in a whole slew of reactions. So I would say there's quite a number of ways. But yes, if you have under the right conditions and they have the right energy, then they will absolutely, you'll get H2 and O. And then you can split them apart. That's the hydrolysis, actually, I think more accurately. So you have to split them, you split the water molecules apart and get the hydrogen out of it and the oxygen. And that's kind of the ideal way to make hydrogen fuel, because you don't want to be carrying around hydrogen gas because it's very explosive. You want to carry around water and then split it apart as you need it. Can it be made on Mars? So they're looking, the big exoplanet kind of search, or the looking for a planet to live on, then technically yes, you can remove all the salt from evaporation. But oh, I got off track and I didn't mean to. Sorry. Mars, thank you. So if we're looking at other planets, we want water ideally to be already there, right? So the water that we're looking for is to save us that trouble from having to go make it. Now, making it requires the things that already have hydrogen and oxygen in them. So you'd have to bring things onto the planet that would have hydrogen and oxygen to make it in the first place. More than that, I actually, I'll look up, they found some evidence of water on Mars, and so that's encouraging. That's why they look for water on all of these planets, because that saves the need to bring all the materials there. Oh, no problem. No problem. Welcome back. On the cap. Oh, yes. Yeah. So that's, and on the polar caps of a lot of the different planets, the constant. So we have ice, as for instance, on our planet, as at the caps, at the polar caps. So that is, that's why they look for water on these planets, not only as a sign of life, but also as a source, so that we won't have to bring any of the materials to make it, which I'm not sure that we would have enough of anyway. So yes, and to answer the salt question, there are desalination plants. That's kind of one option for getting drinkable water, because technically, yes, you can evaporate water and all of the salt will be left behind if you're careful enough at collecting the water that evaporates. Because that water will evaporate, and the steam that comes off, that will be the pure water. But that's a lot of work to do, and it's also it takes a lot of, having salt in your machinery and such it has challenges to overcome. Hydrogen is explosive, but water isn't. Why? Oh, yes, I'm sorry, I missed that question earlier. So hydrogen is, like H2, is a gas at room temperature, kind of standard conditions, and that has completely different properties than water, because it now has a completely different energy, and those electrons that make the atom versus the molecule, no, both molecules, sorry, H2 and hydrogen, those have a different structure, and so they're both stable. So the H2 is more unstable, yeah, and so if you break it apart, it gives a lot of energy off, and then and that is, whereas water is a very stable molecule, and likes to, they make up everything. Good one, very good, very, very good. So that's why, salt, for instance, sodium is a metal, and chlorine is the stuff you probably smell in your pools. I forgot my lab coat today, didn't I? But the chlorine in your pools is the same chlorine that's in your salt, but sodium chloride is a very different molecule than the sodium atoms that make up a metal that's shiny, that you can actually cut with a knife, versus the chlorine that has the very kind of, normal smell. Yes, hydrogen burns to make water. Yes, absolutely. So that's the that's the byproduct in those hydrogen cells for cars and things like that. So the byproduct is water, which is why it's so attractive, because then not only is the energy great, but they're efficient rather, but you get water as a byproduct. So it can go both directions, but it's not going to give you a net energy if you start with water, as I was saying before. So try to be clear on that as well. But great questions, everyone. Anybody have any more questions for this section? Then I'll stop and do the usual upload and then Q&A. Yeah. So if anyone's going to a store to smell any chemicals out of curiosity, they call they call that or there's a